Okay, thanks, Noel. Yeah, so today I'm very glad to introduce our today's speaker, Professor Chen from Caltech. Xie did her PhD in MIT in 2012, and after being a Miller Fellow at Berkeley, she joined the faculty of Caltech at 2014, and where she's a full professor now. She has done a lot of very fundamental works in the area of topological physics, especially topological states of matter and symmetry protected topological states. And she's recognized by many awards, including New Horizons in Physics Prize and Sloan Fellowship. And so today we are very glad to hear about Fracton and Chern-Simons theory.
Yeah, thank you, Xiaoliang, and thanks everybody for coming. So today I want to tell you about something I've been working on in the past 4 to 5 years, which is called Fracton. So Fracton is a relatively new topic in condensed matter. And so I'll try to do a brief introduction to what is Fracton. I won't try to tell the full story. There's a very interesting story behind, but I'll try to show you some examples of what people consider as Fracton and why people find it interesting and very surprising, very exotic and very surprising. And what we have been trying to do to try to bring in Chern-Simons theory, which is a very well-developed field theory technique, to describe a Fracton phenomena and try to learn something about it. And actually we learned something quite surprising about it. So before I start my talk, let me acknowledge my brilliant collaborators. Xiu is a graduate student in my group who did most of the work for this paper. And Wilbur is a more senior graduate student. And then I had a lot of helpful discussion with Meng Cheng and Michael Levin and John McGreevy. Okay, so let me get started. Oh, before that, I want to say that I welcome questions at any time. So if you find anything confusing or want more clarification, just interrupt me. Okay. All right. Okay, so I'll try to introduce Fracton with some simple examples, simple models. So these are maybe the most popular models that people consider when we talk about Fracton. So Fracton started by people noticing that some weird feature happened in these toy models. So these are not experimentally motivated models. They're designed to be exactly solvable, to be mathematically very nice, so we can see a lot of unusual physical properties from there. Okay, so the first one is the so-called X-cube model. X-cube model is defined like this. So it's a three-dimensional cubic lattice, and then there's 1 qubit per every edge, on every edge of the lattice. And then I'm writing these X and Z's, they're referring to the poly X and poly Z matrices for the qubits. So the interaction of this model is actually pretty complicated. The first term involves all the edges around a cube. So there are 12 of them. So it's a 12-body interaction, not realistic at all. The second type are the terms at the vertices and involves 4 edges at the same time around the vertex. So you pick 4 out of one of the planes and then put sigma z on top of it. And of course, the Hamiltonian is designed such that all the terms commute with each other. So when we put all these terms and sum them over all the cubes and over all the vertices, all the terms commute with each other such that we can find we can exactly solve this model and find out about a lot of the physical properties. For example, we can ask, what is the ground state degeneracy? of this model, let's say if we put the model with periodic boundary condition in all three directions, so in X direction, in Y direction, and Z direction, everywhere is periodic. And then in that case, you can exactly calculate the ground state degeneracy and find that the ground state degeneracy follows this formula. Okay, so this is let's try to read it. So this is saying that the log of the ground state degeneracy, it changes with system size. In particular, the log of the ground state degeneracy is a linear function of the system size in all three directions. And then there's a constant correction to that. And this is actually quite surprising because the ground state degeneracy I'm talking about here, this is what we call stable ground state degeneracy, that there's no local perturbation that you can add to the Hamiltonian to easily remove the ground state degeneracy. The ground state degeneracy is topological. Some people would say it's topological in that sense. But despite that, it's a huge ground state degeneracy. The ground state degeneracy is actually exponential in the linear system size, right? D is 2 to this number. So it's a huge ground state degeneracy, and that usually don't happen. Usually we have models that can have stable ground state degeneracy, but that comes from some underlying topological order of the system. For example, we can have a gauge theory of some discrete gauge group. And in that case, the ground state degeneracy is usually size of the group, or maybe size of the group squared. So it's a finite number independent of system size. But in this case, the ground state degeneracy depends on the system size and grows very, very quickly. Okay, so this is one of the surprising things that people noticed by these people when they first proposed the model in 2016. And another thing that's weird about this model is how excitations can be made. So excitations can be made by putting more energy to these Hamiltonian terms. And in particular, for example, if we apply a string of sigma x along a particular line, and we can see that Hamiltonian terms at the vertices at the end of this string will have higher energy, and that's what we usually call quasiparticle excitation. So in this case, we create a pair of quasiparticles, and then we can pull them apart. And we can do the same thing in all three directions, in X, Y, and Z direction. But what's special about this model is that if we apply the string operator in different directions, we actually get different kinds of excitation. So if you look at here, I've color-coded the excitation. This is the excitation of the purple and red term. And here it's the purple and green term, and this is the red and green term. So if we do the same kind of string operator, but in different direction, we actually end up having different species of excitations. And that has a very important consequence, being that if we originally generated a pair of excitation, and then we try to drag one of them and make a turn, make it move in a different direction, then we cannot do that. We cannot do that without leaving something at the corner. Or another way to say is that these quasiparticle excitations, they can only move along a line. They cannot make turns. And that's what we call linear excitations. And this is, again, what's surprising about these fractal models, that it looks like they're doing something like the topological model, that you can create quasiparticles in pairs out of the ground state. But then those quasiparticles, their motions are restricted. And in this case, the motion of these quasiparticles is only along a single line. You cannot make it move in other directions. Okay. And another type of excitation is associated with putting energy into the cube terms. And in this case, what happens is that these cube terms can be excited by applying a membrane operator like this. So on this rectangular shape, we can take all the edges sticking out of the rectangular shape and then put a sigma z on top of it. And then when we do that, we see that the four corner cubes will now have higher energy, and they become quasiparticle excitations. But because these cube excitations, they're always excited 4 at a time, and there's basically no way you can excite them, you can excite a pair of them. And because of that, individually, if we look at each of such cube excitation, there's just no way to take one of them and move it to a different location, because there's no such 2-body process. It's always a 4-body process. So these cube excitations, they turn out to be stuck in space by themselves. And that's what we call Fracton excitations. So when we say Fracton excitation, that refers to point excitation that gets stuck in space, that just doesn't move by themselves. And then when we talk about Fractal models, that's generally referring to models that show up these kind of phenomena. That is, models with point excitations whose motion are restricted, which just the point excitation somehow cannot move freely in the full sample. Okay, so besides these linear excitations and Fracton excitations, there are actually also a type of excitation called planar excitation. And these can be of the following type, where, for example, if we take a pair of the Fracton excitation and we connect them in that way, and this becomes a Fracton dipole, and then Fracton dipole can move in the 2-dimensional plane of the system. And similarly, a linear dipole can also move in a 2-dimensional plane. So when they come in pairs, they have more mobility. They gain mobility in an extra direction, but then they're still not fully mobile in the full 3-dimensional space. Okay, so that's one popular version that people like to talk about for fractons. You already see that these type of models, they embody some very weird physical property. And then people realized that fracton can also show up in a very different context, but with very similar property. And this is the context of so-called tensor gauge theory. Okay, so usually when we talk about gauge theory, I just think about electromagnetism or quantum electromagnetism. And
I'm sorry, maybe before you go to the gauge theory, I have a question about the lattice model. Yeah. Like all these statements here, are they all robust under local perturbations in the same way as in topological order state?
Yes, yes.
So like if I go away from the exact solvable model, like even if I break translation or anything, it will not change.
Yes, exactly. So so first of all, the model is gapped. And then secondly, what we say, the logical operator in the ground space, they all have global size. So there's no tunneling between the ground states by local perturbation. So in that sense, it's topological. Although it depends on what you mean by topological. Some people call it topological, some people say it's not topological.
But basically all these ground states have the same local reduced density matrix.
Yeah. Local reduced density matrix are exactly the same.
Mm-hmm. Thanks.
And Shir, when people say it's not topological, is it for a reason that's kind of deeper than the fact that it has this obvious geometric property, that it scales with subsystem size, or it scales with the size, or is there some other reason why it's not topological?
Right. So by topological, of course, different people mean different things. For band theory, it's the topology of the band. For quantum information people, if you say there's global logical operator, then they call it topological. But some people, by topological, they mean TQFT, topological quantum field theory. And in that context, I would say this is not topological. This model is definitely not described by the usual topological quantum field theory, where you have a vector space that depends only on the topology of the underlying manifold. That's not true. So because the ground space depends on system size, as you pointed out. So it's not just the topology. Yeah. Okay. Yeah. Okay. Yeah, very good question. Thank you. And then let me briefly introduce you to this tensor gauge theory formulation. This is just another popular formulation. Some people like the lattice version, some people like the continuous version. And this one actually gives you gives a very nice intuition about why fracton can happen Okay, so by gauge theory, you can just think about electromagnetism, U1 gauge theory. And usually the gauge theory have are so-called vector or rank 1 gauge theory, where the electric field and the vector potential, they're all vectors, right? Meaning that there are 3 components, X, Y, and Z. And then for the electric field has to satisfy the Gauss's law, which is saying the divergence of electric field is equal to charge density. And then because of this Gauss's law, we have the conservation law, which is saying that the total charge in the whole system has to be conserved. If you have a system without boundary, then the total charge has to be conserved. And if you start from 0, it has to be 0. So if we start from vacuum, and then if we try to create charges, then we have to create them in pairs, right? We have to have an electron and a positron and at the same time. But once they're created, the electron and positron can move because their motion doesn't violate charge conservation. So this is the usual story of what we call the vector gauge theory. And then if we slightly change that and take it into a tensor gauge theory or a rank 2 gauge theory, we can see how fractons can pop up. Okay, so if we consider rank 2 gauge theory, where the electric field now has 2 spatial indices, I and J, and I and J take value in X, Y, and Z. So this is a rank 2 gauge field. And then we can similarly impose Gauss's law on top of these electric field. And because now we have 2 spatial indices, we need to do 2 partial derivatives, partial I, partial J, EIJ, and that's equal to charge density. So this looks very similar, but then the conservation law will be different. In particular, you see that still the total charge is conserved, and also the total dipole in any direction in space are also conserved. And that makes all the difference, because now if you think that we start from the vacuum and try to create some charge configuration, then we cannot just pop up an electron and a positron because that pair carries a dipole. And all we can do is to pop out configurations like this with 4 charges, plus minus. And this configuration has total charge 0 and also total dipole 0, right? And once this configuration is created, this is like the 4-body process that I showed previously for the XQ model. And once you create a 4-particle configuration like this, you cannot just take one of the charge and move it, because that again changes the dipole. So individually, each charge becomes a fractal. Okay. Although once you take a dipole of them, the dipole can move without changing the dipole of total dipole of the system. Okay. So by changing vector gauge theory into rank 2 gauge theory, we see how the charge excitation of the system changes from a freely moving particle to a fractal excitation. Okay, so that's just my very brief introduction to some previous formulation of how fracton can show up. So we played with mostly the lattice model of the fractal model for a while, and then we felt like we need a better handle on things. So that's when we turned into Chern-Simons and tried to see if the Chern-Simons field theory can give us a way to delve deeper into the fractal phenomena. And I'll tell you why we're coming from this, but let me first tell you exactly what I mean by Chern-Simons. Well, usually when we talk about Chern-Simons, we're talking about 2+1D Chern-Simons gauge theory, where we have this A field, these A are vector gauge fields in 2+1D, so it only has 3 space-time indices. And the Chern-Simons term that we write down is like A, dA, and then there's some coefficient in front, and in particular, we know that this coefficient has to be integer. And moreover, if we have multiple A field, if we have multiple gauge fields, so the A has superscript of big I and big J, then there can be mutual Chern-Simons coupling, and this K matrix will encode both the self-Chern-Simons term and also the mutual Chern-Simons term collected all in a matrix. And what we know about the Chern-Simons theory is that this has to be a symmetric integer matrix. Okay, and then apart from that, we can have the normal Maxwell term in the theory. It's just gauge invariant and something we can add. And all together, it describes the Maxwell Chern-Simons theory. Okay, so in 2+1D, this is very well understood. And we know that this gives, for example, when k is equal to 1, that is, there's only one component of the gauge field. And case 1, and this describes the integer quantum Hall effect. And if k is equal to 3, this describes the nu equal 1/3 fractional quantum Hall effect. And when k is a matrix, in this case, a 2x2 matrix of form 0 to 2, 0, and this gives us the Z2 gauge theory in 2 dimensions. Okay, so it's very well understood that these abelian Chern-Simons theories give us a complete and very nice description of abelian topological order in 2+1D. But we are thinking about models in 3+1D. The previous model, the lattice model, and also the gauge theory model I told you about, they're both in 3+1D. So we're looking into possibility of Fractal phenomena in 3+1D. So we need to generalize what we have on the previous slide into 3+1D. So one natural way to generalize the gauge theory in 2+1D to 3+1D is to make the gauge field 3+1D, is to increase the space-time indices from 3 to 4. But here we choose to do something differently, and I'll tell you why. What we choose to do is to keep the space-time indices still to be 0, 1, 2, or time and x, y. So the gauge fields are still 2+1D gauge fields, not 3+1D gauge fields. But instead, we try to make the theory look three-dimensional by choosing to have these indices of the gauge field to go from -infinity to +infinity, right? So if we have only a finite set for the big I and big J, we're in 2+1D. But now we're extending it to infinity with the hope that we'll end up with something that's 3+1D. And the reason we're doing this is because they're very simple situation where it works well and it has connection to fractal. And that is the situation where, for example, the K matrix is very simple, it's just diagonal. So everything that's off diagonal is 0. But the diagonal entries are all the same and they're, let's say, 3. Okay, so in this case, each gauge field coupled to itself through the Chern-Simons term. And we know that in this case, the system that's being described is simply a pure stack of nu equal 1/3 fractional quantum Hall. And because the indices goes from -infinity to +infinity, so we're describing an infinite stack in the thermodynamic limit. So this is well understood. And this is also, of course, this is a very, very simple model from the theoretical point of view because we understand everything about nu equal 1/3 fractional quantum Hall. And if we just stack them together, at least when the coupling between them is very weak, then all the layers are gapped. So any small perturbation on them are irrelevant. So we know everything that's going on in the model. And so this is something that's not going to be very surprising. But on the other hand, this is a model that already embodies some of the surprising Fractal phenomena that we've seen previously. For example, the ground state degeneracy of the model. The ground state degeneracy of the model will scale as 3 to the nth power, where n is the number of layers we have. So that's an exponential ground state degeneracy. But of course, that's natural just because each layer will contribute a ground state degeneracy of a factor of 3. And then the quasiparticles, the point excitations in the system, they will move in xy planes only, meaning that all of the quasiparticles, they're planars. And they cannot hop in the vertical direction because the coupling between the layers are irrelevant. So if you just stay in the decoupled limit, Nothing can help in the third direction. And then I didn't talk about entanglement previously, but entanglement is also a very important feature in fractal model. And in particular, if you take a region, let's say a cylinder in the system, and calculate entanglement entropy, then apart from the leading area law term, there will be a subleading term. And here the subleading term will be linear in the height in Z. Okay, and it's also easy to understand why it happens here, because here we have a stack of fractional quantum Hall, and each layer of fractional quantum Hall will contribute a subleading term in the form of a topological entanglement entropy. So when we add them up, the entanglement for the cylinder would have a subleading term linear in the height of the cylinder. So we would say that in some sense, this simple stack of a fractional quantum Hall is already a Fracton system. Usually we wouldn't call that, but if we want to say, we want to use the definition of Fracton, we would say that this is a Fracton system. But of course, this is a rather trivial type of Fracton, right? It's just a stack, and we understand everything about it theoretically. And the question would be to say, can we get something more non-trivial? Can we get something more interesting out of this formulation? And then we just go to the next thing, which is to say, okay, let's not just populate the diagonal, and let's populate the next diagonal. And for example, we can still keep the diagonal to be 3, and then make the next diagonal to be populated with 1, and everywhere else it's still 0. So everywhere that doesn't have a number is still 0. Okay, so this is of course still a legitimate K-matrix. Is integer, it's symmetric. And then the question to ask is, what kind of physical system is it describing? Is it a fracton? And if it's a fracton, what kind of fracton system? And it turns out that these type of K-matrices has already been studied back in the days, in the 90s and 2000s, where people were thinking about a 3-dimensional fractional quantum Hall system. And the proposal is that, let's say we start from a stack of fractional quantum Hall system with nu equal 1/5. Of course, there are lots of experts here about these kind of systems. So if I miss anything, please let me know, miss any references. These papers, they were proposing that if we start from a stack of nu equal 1/5 fractional quantum Hall, and then we make the layers get closer to each other. And then when that happens, these layers will be coupled, and the electrons, they will try to avoid each other even though they are in neighboring layers. And that introduces, in terms of Laughling's wave function, that introduces some mutual zeros in the wave function. That's where this off-diagonal ones come from. And back in the days, people already understood a lot about the system. For example, there's something quite unusual in terms of the fractional charge that's happening in the system. So each layer has a fitting fraction of 1/5, but when they're coupled by these transcendent terms in this way, then the distribution of the fractional charge for the quasi-particles actually have a very exotic shape. For example, if you introduce a flux in one of the layers, that's what we do in fractional quantum Hall. We introduce a flux and ask how much charge is accumulated on that flux. And here, because we have an extensive system, we can not only ask how much total charge is accumulated at the flux, we can also ask how that total charge is distributed across the layers, which is to say that starting from this flux in a single layer, we can talk about how much charge is accumulated on all the other layers. Okay, and it turns out that this is an irrational number when the system size goes to infinity, and this is it goes exponentially small when you insert a flux here and then go away from the layer, but then it never reaches exactly 0. right? It just exponentially decay, and it decays in this irrational sense. And of course, that translates into the irrational statistics. If we have a flux in this layer and another flux in that layer, and when we break them around, they see the fractional charge attached to each other in that particular layer and translates into this mutual statistics that I write down. Okay, and another thing that we can try to compute is the ground state degeneracy of the system. So originally, if we just have a pure stack of nu equal 1/5 fractional quantum Hall, the ground state degeneracy is very simple. It's 5 to the number of layers, right? 5 to the n. But now, if we try to calculate the ground state degeneracy of this huge K matrix, it becomes very complicated. There are multiple terms. And then if we take the limit of system size being big, then this approaches an exponential form, but the base of the exponential form is again an irrational number. Okay, so this is very surprising. Now, usually we've seen in previous examples that we can have exponential scaling of ground state degeneracy, but it's always like 2 to the L or 3 to the L, 5 to the L. But now we have, at least in the limit, we have irrational number to the L. Okay. And then we can further ask what is the fusion group of all the fractional excitation, because this is still everything is abelian, and the fusion gives you a group. And the fusion group turns out to be of this form. The fusion group has two parts. It's a tensor product of two cyclic groups. And the first cyclic group has order the Fibonacci number. And the second group has order 5 times the Fibonacci number. Okay. And all these are very, very weird if we compare it to what happens in the XQ model. So let's go back and look at what happened in the XQ model, then we'll see why this model is so weird. Okay. So this is the XQ model. This is the Hamiltonian.
Sorry, in the fractional quantum Hall model, is there anything that can move in the z direction?
No, and at least not so. So the quasiparticles
there is a coupling,
are all...
there is a off-diagonal term, but still all the particles are moving only in the plane.
Yeah, all the particles are moving in plane. They're planars. Yeah. So the particles might have a larger profile. It may distribute over several layers, but then their motion is only in plane.
I see.
Okay. So let's compare to what happens in the XQ model, and this is the XQ model I showed you previously. So in the XQ model, and let's compare to what the planars are doing in the XQ model, because in the quantum Hall case, in the Chen-Simons case, we only have planars. We only have things that move in the planes. So let's not look at the Fracton part or linear part of the XQ model, but only look at the planar part, which is the Fracton dipole and the linear dipole. Right. So Fracton dipole are generated by a string operator like this, and linear dipole are generated by string operator of 2 sigma z or 2 sigma x. Okay. Okay. So for example, we can ask what's the fusion group of the Fracton dipole and linear dipole, and obviously all these planar excitations, they have a Z2 order because the string operator are Pauli operators. So if you have 2 copies of them, they fuse into vacuum. So each one has order 2, but then in each layer, we can have Fracton dipole. In the next layer, we can also have a Fracton dipole. So altogether, there are lots of Fracton dipole generators. Where's my mouse? Okay, here. In each layer, there is a generator. There's a Fracton dipole generator and a linear dipole generator. And altogether, there are a lot of generators, but each generator has only order 2. And that's very different from what we see previously, because in the Chen-Simons case, let me just back off. we have a fusion group where we only have two generators, and each generator has exponential order. Each generator needs to be fused many, 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 many times in order to go back to identity. Okay. And then if we calculate the statistics between the Fractal dipole and the linear dipole, we find that it's mostly pi if they're next to each other, because these are sigma x and sigma z. So all you can get is a -1 out of there, which is to be compared to the irrational statistics that we've seen in on the previous slide. Yeah, so this is not irrational at all. This is rational. And again, the ground state degeneracy of the model scales very nicely as 4 to the power of n, of course, because, it's 4 to the power of n with integer basis, while in the previous case, we have irrational number basis for the scaling of the ground state degeneracy. Okay. And for the XQ model, actually, we have a pretty nice interpretation of why things go this way. And this is what we call the foliation structure of the XQ model. That is, if you think about the XQ model, if we compare the XQ model on a slightly smaller system size to the XQ model on a slightly bigger system size, they will be different because, first of all, the ground state degeneracy will be different, but the difference can be completely captured by a decoupled layer of 2D topological order. In this case, is the 2-dimensional toric code. Sorry, I should have spelled that in full. But this is 2-dimensional toric code, the 2-dimensional Z2 gauge theory topological order. So for the smaller system size part, if we just add this 2-dimensional layer anywhere in the middle of the system, because I have periodic boundary condition in the Z direction. So I can add this layer anywhere in the middle of the system and then do some smooth deformation around the layer. And then I can fuse this layer into the bulk so that the bulk now look like it's the original model, but on a slightly bigger system size.
So if I do this foliation again and again, does that mean that the XQ model is topologically equivalent to layers of toric code?
Yeah, a great question. So this process is reversible. You can go from left-hand side to right-hand side and right-hand side back. So if you start from a big system, like you said, you can start decouple these layers out, right? You can decouple 1 layer, 2 layer. But the thing is, you cannot completely decouple it. At the end, it doesn't go completely into decoupled layers, because if it does, then the system will be totally trivial. So it's like toric code. Toric code, if you start from a bigger toric code, you can take product states out and you can make toric code smaller, but then you cannot say toric code is equivalent to a product state. So it works when you still have a pretty big system size and you're just looking locally at 1 layer or 2, but you cannot do it to the end. Okay, right. So this structure already explains a lot of the non-trivial feature that we see in the XQ model. For example, the ground state degeneracy scales as 4 to the n without let's forget about the constant correction for now. But if we only look at the exponential part, it's 4 to the power of n. And that's very easy to understand now because all these 2D toric code layers each comes with a ground state degeneracy of 4. So when we stack them, there's this scaling. And then the planons have finite order and they all have order 2, and that's because the planons come from these 2D toric codes. And the toric code contains quasiparticles of order 2, so all the planons in XQ have order 2. And then the statistics are like pi statistics. And moreover, the statistics don't go very far. They're like, if you have a Fractal dipole and linear dipole next to each other, there can be pi statistics. But if you move further away, the statistic will be 0, right? And that's easy to understand because when they're near each other, the planons come from the same 2D toric code. But when you move them apart, they come from different 2D toric code, so they don't have statistics anymore. Okay. And because of all this, and then if we compare it to the Chern-Simons theory with diagonal being 3 and off diagonal being 1, not off diagonal being 1, but the next diagonal being 1, then we see that that's very different, and it doesn't have these nice properties at all, which means that this 131 K matrix does not represent a foliated Fractal system. If it's foliated, it should satisfy all these previous properties, where ground state multiplied by a factor of integer when they grow, and then the planars will have finite order and short range statistics, but all these things are not true for this 131 K matrix. Okay, so the reason we actually originally wanted to look at these infinite dimensional K matrix and the Chern-Simons theory was because we wanted to study foliated fractal model, because we noticed this foliation structure in the XQ model. We try to look into what other possibilities there are, and then we can just do so much with exactly solvable models. So we were hoping that by turning into field theory, we will be able to do more. And that's doable, meaning that indeed within this infinite dimensional K matrix Chern-Simons formulation, we can also find examples that represent different foliated fractal model. And those were actually our original motivation, although then we found that there are all these non-foliated ones. So here, let me give you an example of what is a foliated K matrix. So here, this one is populating more diagonals, populating 5 of them. And then if we take the inverse of this particular matrix K to K inverse, and this encodes fractional charge, statistics, and all that, and it looks like this, okay? And then we can read from the K inverse about the statistics between all the quasiparticles. Some of them are like 2 pi over 4, some are 2 pi over 2, etc. And this, we can compare it to what happens to the 131 K matrix, and we can immediately see that the structures are very different. So if we take the 131 K matrix and take the inverse of it, and you see that it's populated everywhere. And of course, this is for a particular size, and I can make the size bigger, and then the inverse would look different. And of course, what happens is that the entries will decay exponentially away from the main diagonal, and that corresponds to the decay of statistics and decay of fractional charge attached for the quasiparticles. Okay, and of course, the difference between the foliated case and this non-foliated case is that in the foliated case, you see that the statistics become exactly 0 from a certain point on, while in the non-foliated case, it never exactly goes to 0, and that has to do with the non-short range of the statistics between the planars in the model. Okay, and then back to the foliated case. So this Chern-Simons formulation allows us to, for example, determine that indeed we can find a foliation structure, meaning that if we try to make the system smaller or make it bigger, we can either extract a 2-dimensional plane of topological order out, or we need to add an extra layer of 2-dimensional topological order. And in this case, this is done not by doing local unitary like what we did in the lattice model, but instead we know that for this Chern-Simons theory, for the K matrix, there are these SL transformations. And these SL transformations, so this is a particular SL transformation that we designed such that when we apply this to the K matrix in this way of W transpose KW, That's how we reorganize the gauge fields and then do transformations on them. Then what we see is that we can decouple certain layers out. We can decouple a 4x4 block out. And that 4x4 block exactly corresponds to this extra two-dimensional layer that we have in the foliation structure. And then if we remove this 4x4 block and recollect all the other dimensions, the K matrix goes back exactly to itself, but with a smaller size. Okay. So this is how we find the foliation structure of this particular K matrix. Okay, and in general, we would hope that this infinite dimensional K matrix will give us a handle to more systematically study the foliation structure in all these kind of systems. For example, given two K matrix, we want to understand how they are, first of all, whether each of them are foliated, and if each of them are foliated, whether they are related by just adding some two-dimensional block and then doing some local transformation on top of it.
So just a comment. I don't know if this is the case, but if I make an analogy, if I look at the K matrix as if it's like a single particle type binding model Hamiltonian, then it looks like the special case of foliated is like some case with flat band, like where you can find linear functions with finite support. And then the more general case is you can only find the exponential decaying function.
Yeah, in some sense, yeah, exactly. Although this is some analogy we try to draw upon, meaning the similarity between K matrix and the Hoping matrix. But on the other hand, K matrix are very different. It comes in a totally different mathematical structure. For example, you cannot do small perturbation on K matrix. All entries are integer. And secondly, when we do transformation, it's not unitary transformation, it's this SL transformation, which works totally differently. And that's what we find very difficult to work with. Well, we don't understand much about the mathematics, so we're trying to talk to mathematicians, but it turns out that they know something, but it's not like they have completely figured out about these infinite dimensional symmetric integer matrices under these kind of classification schemes. So, yeah. All right, so this is if we draw a figure for it, and this is what happens for this particular model, that we start from a slightly bigger system size, then we do this deformation represented by this W matrix, and then it becomes slightly smaller together with a decoupled two-dimensional layer, and this is a twisted Z2 cross Z2 gauge theory, but just some two-dimensional topological order. Okay. And I want to emphasize that this W matrix, it looks pretty big, but it's a local transformation, meaning that any non-trivial transformation is inside this blue block, and everywhere else is just identity. So we're only doing transformation close to this layer that we're decoupling out. Of course, then we can keep doing it in other places and decouple out more layers. Okay. So when did we start? 15, right? Yeah, okay. Okay. So this is what we are trying to, I'll give you some illustration of what we are trying to do with these infinite dimensional K matrix and how we're trying to extract Fracton physics from it. First of all, it gives us examples beyond what we see in exactly solvable models. And for the foliated ones, we're hoping to identify more examples and calculate their properties and study the equivalence between them up to this foliation structure, up to inserting of two-dimensional layers and doing transformations like that. And then for the non-foliated ones, we have a much less understanding in terms of, we don't understand how to define this equivalence class at all. But we're at the stage of just trying to identify examples and calculate their properties and try to make sense of what's going on in them, because if we compare system of different size, it doesn't look like they differ by two-dimensional layers. So how do we even start to think about a question? Think about the problem is an open question. Okay, but first, if I have some remaining time, but first, just to be completely sure that we're doing something legitimate, we need to go back and address some more basic questions. This has to do with my uneasiness of working with field theory, that I want to see everything on lattice, and then I know exactly about locality. So what we did is to try to come up with a lattice model realization of these field theory representations. So of course, these are not exactly solvable model because we're trying to go beyond that, but we were able to come up with a lattice construction that we can be satisfied to say that, okay, everything's local, everything's safe, and we can draw a conclusion about, for example, whether the model is gapped, or if it is gapped, then we can talk about the profile, the locality profile of the quasi-particle excitations, and understand that. For example, we don't want the quasi-particle excitation to be secretly string excitations. And that we found that sometimes that can happen if we don't have a well-defined model. So that's what we spend a lot of time doing. And basically, we were able to address this question to our satisfaction, of course, within a set of K-matrix that we're interested in. And of course, back in those papers about three-dimensional fractional quantum Hall, people were already able to address these questions to some extent in terms of Laughlin wave function. So if the K-matrix correspond to a Laughlin wave function, then it's physical and it's nice. But of course, we try to do things in a more general way, so we don't want to rely on what Laughlin wave function. For example, we can have negative entries in the K-matrix. So we try to consider more generally what's called a quasi-diagonal K-matrix, meaning that K-matrix where we have entries close to the diagonal, but within a finite distance to the diagonal. And that's what we call a quasi-diagonal K-matrix. And they can be positive, negative, zero entries. And so as long as we focus on K-matrix that's quasi-diagonal, we show that there's indeed a lattice realization. And we can calculate the spectrum. Well, the spectrum is a field theory calculation. It's not exactly solvable model. So we did a field theory calculation, and then we can figure out about the shape of the string operator, or the profile of the string operator. So we can indeed say that the excitation is a point excitation, not an extensive excitation in the z direction. And that is a very important thing for us to understand. Okay, so I'll very quickly give you the basic idea of how we did this construction. So basically, we started from a stack of integer quantum Hall. So each layer is just an integer quantum Hall. And we imagine that there are a bunch of planar symmetries, meaning that the integer quantum Hall, the fermions in the integer quantum Hall, carry charge under different U1 symmetries. For example, the first three layers carry charge under A1, and then starting from 3, 4, 5 carry charge under A2, and 4, 5, 6 carry charge under A3. So when we do this, we couple the integer quantum Hall layers to a dynamical background gauge field. So we make these A1, A2, A3 into dynamical gauge fields, and then we can, in a sense, integrate out the fermions. So this is what happens in the Lagrangian. Start from a bunch of integer quantum Hall, and we couple them to external gauge field, and then we make the gauge field dynamical, and then we integrate out the fermions. And when we do that, sorry, I didn't write it out, but when we do that, in this particular case, we end up with the 131 Chern-Simons term for the A field. And here I'm just writing out all the lattice terms, and then there's a fermion hopping term and coupling to the gauge field. And of course, in the lattice model, we don't remove the fermions, but just keep them there. But the idea is that this lattice model is supposed to represent what is happening in the Lagrangian. So here in this particular configuration I'm drawing, if we integrate out the fermions, then the A1, A2, A3 gauge field will couple as the 131 K matrix. You can see that the self Hall conductance comes from 3 layers, so it's 3, and then the mutual Hall conductance comes from the overlapping 1 layer, so it's 1. So for any K matrix of this form, we can come up with a configuration such that we can reproduce the K matrix using this construction. Okay, so I won't try to bore you with all the details. I think I'm running out of time with all the details of the construction, but I want to emphasize one point. Sorry, I want to emphasize one point. I didn't write it here. That the profile of the quasi-particle excitation in the z direction is related to the K inverse matrix and how entries decay in the K inverse matrix. So if entries become exactly 0 in the K inverse matrix away from the diagonal, then the quasi-particle will have a sharp edge in the z direction. So it has a it will be exactly 0 beyond a certain distance. But if it decays exponentially, like in the case of this 131 matrix, then the profile also have a exponential decaying tail, but it's still local in that sense. It's still local in the sense that it's very fast exponentially decaying tail, but it never goes exactly to 0. Okay, but that gives us confidence to say that these are quasi-particle excitations, not string excitations. Okay, and then the spectrum of this model has to do with the eigenvalue of K. This is just a field theory calculation that the gap of these gauge fields is proportional to the smallest eigenvalue of K squared. Okay. And so, for example, the 131 will be a gap case, and 141, 151, 151, all these cases are gapped. But if we have 101, 111, and 121, these cases are gapless. So the gap case, they pretty much are similar to what we see in 131. But if we look at the gapless case, they can look very different. And we're still trying to figure out what's exactly going on in the gapless case. For example, are these gapless modes stable? Do they have some instability to symmetry breaking or other things? Or if they're stable, are they some kind of gapless spin liquid, or even beyond gapless spin liquid, gapless Fracton system? Okay, so let me try to summarize what we did. So we were looking at these Chern-Simons theory with infinite number of components for the gauge fields, and for the cases where the Chern-Simons terms are described by quasi-local K matrices, we can have a nice lattice construction for all these models, meaning that everything's local, everything's legitimate. It's a physical 3-dimensional model, and then we can have some idea of what the string operator looks like for the planons, and then we can figure out whether it's gapped or gapless, and we can come up with examples of gapped foliated models and gapped non-foliated models, and even gapless models. And open questions, I already mentioned many of them. For example, given the K matrix, how do we know if it's gapped or if it's gapped foliated or gapped non-foliated? And if it's foliated, how do we determine the equivalence class in the sense of equivalence class for infinite dimensional symmetric matrix? And then what about the non-foliated models? How do we think of how does the degeneracy go, and how does the fusion group go? And in particular, how do we think about the the renormalization group transformation. And by renormalization group transformation, I mean something like the foliation structure. The foliation structure is basically how we try to imagine what changes in the system when we make the system bigger or smaller. So for the non-foliated case, that's a very puzzling case. That we need to understand what's changing when a system becomes bigger or smaller, or in a sense that you are integrating out shorter distance physics. Okay. And finally, what does gapless matrices represent? That is also open. Okay. And finally, non-quasi-diagonal ones. And actually, I want to comment that the XQ model does not exactly fall into this formalism, because it has fractons and because it has it's actually described by some non-quasi-diagonal ones. So that's just saying that we may need to also go into for now we're restricted to these quasi-diagonal ones, but it also makes sense to look into the non-quasi-diagonal ones to think which of them are legitimate and which of them are, and what kind of physics, what kind of fractal physics they're describing. Okay, that's a lot, and that's all I want to say, and thank you.
Thanks. Yeah, a very interesting talk. So let's have some more questions.
I have a question. Do you see these things be applied in quantum error correction codes?
Yeah, good question. Well, the XQ model and even the Haas code, which I didn't mention, which is
these like people constructed them like with the motivation and idea on quantum error correction behind. So these more complicated ones, like, do you see them having potential in being applied as quantum error correction codes?
I haven't thought about it and don't know anybody has thought about it. It's a great question. And how can we make use of irrational statistics? Yeah, a very interesting question. So yeah, let me know if you figure out anything.
Sure.
Can I ask a very basic question?
Sure.
So in taking the thermodynamic limit, is it well defined at all to try to, take in the field theory to take a continuous limit of the direction transversal to the foliation, meaning you wrote, Chern-Simons terms layer by layer, you have a discrete sum. I imagine there are serious abstractions in, writing the sum as an integral, but, does it make sense at all to try to do that?
Yeah, great question, because this is one of the things that people struggle with Fractal, which is to say how to write it as a field theory. And it's not obvious because, for example, in the XQ model, it's already a big problem because the ground state degeneracy scales with system size. And if you just naively say, okay, let's shrink the lattice constant to 0, then the ground state degeneracy becomes infinity. And how do you deal with that? Yeah. So there are ways to deal with it. And I will refer you to papers by Natty Seiberg and also Kevin Slago and maybe probably many other people. So I think one of the idea that I learned from Kevin is to put in a so-called foliation field like putting some field that gives you the underlying foliation structure and to go from there. But I would say that how satisfied the field theory people are, we need to ask them because these are very weird models, and they're highly, there's certain feature that highly depends on short distance physics. So it depends on what you want to do.
Yeah, you also mentioned doing RG flow. Indeed, right. It's a very tricky thing, I guess, because of this foliation structure.
Yeah, by RG, my RG means lattice RG, and so I'm not doing RG in the momentum space. Yeah, but of course, whether this can be interpreted as a momentum space RG, that'll be great to know. And I'm doing what we are doing on the lattice is mostly a fixed point RG. It's mapping fixed point zero correlation length state to zero correlation length state. And even at fixed point, we don't know how to do it for these non-foliated models.
Thanks.
What happened to screw dislocation if I have the 131 model?
Oh yeah, we wrote a paper about this recently.
I see.
For the XQ model. So I guess your starting point for thinking about screw dislocation is because there are these layer structure, right?
Yeah.
And indeed, so in topological insulator, if you have a screw dislocation, there will be chiral modes flowing along the screw dislocation. And very similarly here, we expect, for example, if the foliation structure is composed of chiral topological model, then the screw dislocation might also carry a chiral mode. In the paper, we didn't do that. We did it for the X cube. So we put a screw defect inside the X cube. So the X cube, the foliation layers are non-chiral. So you wouldn't expect any chiral modes, but we do see the change in ground state degeneracy associated with screw dislocation. Basically, so for example, one thing we notice is that the screw dislocation, because it connects the planes, it gives extra motion to the fracton. Somehow the fracton can start to hop because the fracton comes in and then the planar can wind around and go above. It's hard to describe, but basically it gives fracton, which originally cannot hop, it gives it motion along the screw defect, and those kind of things gives rise to extra ground state degeneracy.
I see. So it's not breaking the ground state degeneracy. It's giving you extra ground state degeneracy.
Oh yeah, it gives you extra.
I mean, naively, if I think about the layers of integer layers of fraction quantum Hall, like 3330, and no coupling between different layers, then if I introduce a screw dislocation, let's say a pair of screw dislocation, then all the different layers are connected. So suddenly I get okay, maybe that's true. I'm trying to say that change the ground state degeneracy, but I guess probably it also then.
So this case is like so for screw dislocation we have to put it on open boundary condition. We don't know how to do a periodic boundary condition. But with open boundary
you can do a pair. You can do it.
You can do a pair, yes. But let's say open boundary condition, originally there's no ground state degeneracy. But when you put in the screw defect, then you actually can have this line that goes around the screw defects that actually gives you extra ground state degeneracy. So if you have a pair of it, I haven't thought.
I guess if you have periodic boundary condition in the XY direction, then you have pairs of screw dislocation. You will connect the different torus into a different manifold. So so maybe you'll also generate additional.
Yeah, I see why you're saying that. So that's definitely a possibility. And I think there's another paper by Natty putting the XQ model on some twisted boundary condition. So in a sense, similar to what you're saying, that different layers will connect around the torus and moving to another layers. And they also see changing ground state degeneracy because of that. I think in that case, you will have, fewer ground state degeneracy, depending on how you connect.
Any other questions? Okay, if not, let's thank Xie again. Thanks very much.
Thank you.